So our next part is the panel discussion. And yeah, as we mentioned before, like there are two ways for asking questions. The first is that you can directly ask a question via the Zoom. There's a chat button there. So you can put your question in there. And also like you can raise your hand and we can unmute you to let you ask questions. And another way is that you can go to the Slido website and you can put your questions there. Okay, so, and yeah, in the panel discussion, we have four, the first speakers here, Professor Alan Yu, Professor Aleksander Madry, Professor Earlence, and Professor Matthias. So yeah, let me unmute the Alan first, sorry. Or Xin, can you unmute Alan for speaking?
Yeah, I unmuted Alan, I think.
Okay, you can hear.
Yeah, we can hear you now.
So our first four speakers are here, right? Like.
I think so.
Okay. So maybe let me start the question. Like for Alan, your talk is about the occlusion. For Margaret, your talk is about the dataset statistics between like different datasets. And the Earlence, you're talking about the adult tags like on object detectors. Professor Matthias, you're talking about the generalization, how to test that. Like, do you think like these questions in the high level, like they're really looks quite different to your testing scenario? Do you think like they are closely connected or? Yeah. So Alan, can you start first?
Sorry, I had there was a small cutout in the middle. I mean, you're saying that the talks were rather different?
Oh, no.
You're saying?
Oh, I'm asking like, for example, you're talking about the occlusion things, right? And the Professor Madry are talking about some dataset statistics. And Professor Earlence are talking about the attack on the object detector. Professor Matthias are talking about testing generalization. Like, can this question all be like in high level related, say, because your testing scenario are quite different, like, and like, do you think like they are closely related to each other?
I guess I can start just to get things going. I mean, I would say that they relate fundamentally to the enormous space of images and the fact that the data sets individually are not big enough to deal with them. And we have to come to terms with all these issues. And the adversaries are a very nice way to effectively expand the space of images that we're testing on. And I think that's extremely important aspect of vision. So what do the others think?
Yeah, just to add on this, like, so to us, like, like, okay, to me, the question of robustness is the question, like, how to learn reliably using our tools. And for that, like, we need to understand, how much of this is coming from our training methods being not appropriate versus, like, there are us hitting some fundamental barriers in terms of how our data sets are constructed. Right, so this is where our work came from, just saying, okay, before you try to innovate over adversarial training or something, like, just understand what are the limits of what our models are able to learn from the data sets we are testing them on, and how does it differ to like how humans learn, because in the end the question of robustness is really the question of like how different machine learning kind of vision is, like how much does it differ from human vision. So to me, trying to go all the way to the core and thinking about like what can we even hope to learn from this given the bias that exists there, that was where our work fits into.
I see. So Professor Earlence, do you have any like comments on this question?
Yeah, I think, I mean, I kind of agree with what was said already. I mean, especially from a, from an attack perspective, in a sense, like I view all these attack algorithms as kind of data generators, in the sense that, okay, we get a sense of what these attacks are going to look like, and maybe in terms of these images, and that can probably be helpful in studying how our natural training sets that we collect today, how they might be different from what these attacks look like.
I see. Then Professor Matthias, do you have any comments on this question?
I think I would add that I think one of the maybe biggest discrepancies is that we tend to use discriminative models most of the time when we train on ImageNet. And the type of tests that we are doing, like occlusion and so on, they actually use quite explicitly the qualitative physics of the world, right? And I think that also the way how we generalize is by understanding particular, like the grammar of how objects can be combined to new objects and so on. And this is not very well represented in the typical architectures that we are using. And so the non-robustness properties that we are seeing, I think, is due to a lack of capturing these qualitative physics, these visual grammar type of aspects that would allow to generalize, and also completely out of domain.
Yeah,
I see.
I would second that. I mean, I would go ahead with that, and I'd say also, for me, a problem with the current data sets is that they set up a situation where people just try and train discriminative models because they're able to deal with them. But really, if you go out of domain or do harder things with more complex adversaries, then you're giving it a far harder task. And this is my bias, but my long-term perspective is we won't solve vision until we have good generative models. And we ought to be having data sets or tasks that would evaluate those rather than methods that you can solve purely by doing regression. We know how to do regression, but it takes us some way, but it doesn't take us nearly far enough.
I see. So, okay. So we saw one audience email from University of Bristol ask a question. I'll unmute you so you can ask your question there.
Thank you very much. My question is related to the pipeline that Professor Madry had presented about how datasets are created, which is we have one task, we choose certain concepts, and then we go and search for examples that allow us to create a balanced dataset. There is currently two new trends. One is to collect one dataset for multiple tasks, like the taskonomy approach. Another is collect data for no tasks. So just collect as much data as you have and then see what you can create with it. That, though, results in clearly unbalanced datasets. So datasets such as Elvis for the latest one for segmentation. We created a dataset on video understanding. So that gives you a rich dataset in the sense of data is collected before tasks are decided, but the unbalance automatically happens. What do you think about this alternative? Is it a way to go, or is the balance a critical requirement?
Yeah, so that's an excellent question. And, so I definitely, so the problem here is that our current data sets is they're convenient to have them balanced for many reasons, but just this balancing alone is already it's not ecologically valid. This is not how, our vision works. We don't see that many breeds of dogs. Probably I have seen maybe at most 40 different breeds of dog in my life, essentially as a human. So essentially, so it would be an interesting approach where we kind of imagine you kind of record a video of a human walking around the town for a week, and based on that you create a data set. So we are not creating this ourselves, but this would be a very interesting approach to do it, because it definitely would get closer to this kind of ecologically valid way of data set construction. So yeah, I like this idea.
Okay. Yeah, so we get another question from Nathaniel Ruse. So you can ask your question there. Thanks.
Hello, my name is Nathaniel from Boston University. This is a question for Professor Bethge. So my question is, there are some other classes of kind of machine learning algorithms such as capsule networks proposed by Jeffrey Hinton. This is more like a question about your intuition about the future, is whether we need these new classes of algorithms or whether you know, fixes such as getting data sets like stylized ImageNet and the invertible deep networks would kind of fix the architectures that we have right now to more closely model human perception.
I don't think that like data augmentation alone would solve the problem. Obviously, I guess nobody knows. I think if one can get quite a lot of improvements by providing more information, maybe by, for instance, by introducing semantic bottlenecks, doing attribute learning and trying to learn intermediate features that are more generally useful. But I guess my personal hunch is that I think it's also necessary, or at least very promising, if we make progress on building different architectures. I mean, one thing that is quite obvious is that, for instance, the background information that we tend to use in a rather similar fashion in these discriminative architectures, it would be very good to segment them out and do this in a very principled fashion in typical object recognition tasks. So we have a clear distinction between foreground and background. And that's just one of the many things that we know and that we have worked a lot with, but we haven't fully translated into, say, effective architectures that do this on a general basis. So okay. I guess I think like using generative modeling ideas will improve and will be important for building better vision models.
Okay, thanks, Professor Matthias, for answering this question. We are asking, watching, is that you? Or like,
yes.
Yeah, you can ask a question there. Yeah, thanks.
Yeah, thank you, Chihan. So my question is regarding domain adaptation and how this technique will fit into this panel discussion. Given the background, Professor Madry talked about dataset bias and model bias and real-world application. The translation has been a long-standing problem domain adaptation tries to solve. The way it does it is to review some unlabeled data of the target domain during the model training stage, such that the model could potentially account for the target scenarios. Not only the dataset bias, also want to see how domain adaptation could fit into the adversarial robustness in general. Thanks.
Yeah, so I'm not sure there was a particular person that was supposed to answer, but like, let me just take a stab. Yes, so in some ways, yes. So again, so maybe one thing to say to set the stage that like what we discover in our work is that actually like in some ways, instead of thinking of robustness as an end goal, you can really view as robustness as a way of like trying to understand, you know, how different, you know, the way machine learning models solve the given task is to how humans would solve it. And kind of adversarial example in particular are a way of seeing the difference. Like essentially, whenever you figure out some correlation, some bias of the model that humans don't have, that kind of is likely to give rise to adversarial examples. So to me, for example, adversarial training is all about, you know, encoding kind of stronger human-aligned prior into the model. So domain adaptation would be another way to do this, you know, like kind of essentially by domain adaptation, even though you use unlabeled data, you kind of tell the model how the world outside of the distribution it has seen actually looks like. And, you know, this is in particular, like the important, you know, goal of the models is to get disentanglement of certain features. So you would like to really like kind of, it had this kind of higher level representation of like, what are objects and, you know, what is background and so on and so on. And essentially like providing more information via domain adaptation could be a very viable way to do it. So in particular, we do know that you can leverage unlabeled data as a part of the serial training to get more robust models. But I think there is more to be done there, exactly by building on the domain adaptation work.
Okay, yeah, thanks for Madry for asking this question. And we got one question for the Professor Earlence. There's one question from the Slido asking, have there been like security incidents in the real world where a bad actor can use, say, adversarial eyeglasses or stop sign stickers to fool facial recognition or self-driving cars? Do you know any such things happened before?
So there are a few interpretations to that. I mean, one interpretation of the question is, has there been a real security incident of some malicious person trying to do this attacks on face recognition or other things? To my knowledge, no. I have not heard of anything like this. However, there are several demonstrations coming up. They may not be exactly adversarial examples, but they do demonstrate some end-to-end effects. So one example is this attack I saw a while ago where they make a 3 look like an 8, like a 30 speed limit. They put a tape and extend it out. It's not exactly your adversarial example in kind of the definition that we have kind of borrowed from the digital world, but it does show an effect, an end-to-end effect in some sense. But beyond that, I do not know of any actual malicious attacks in the style of adversarial examples that that we think about here in these papers.
I see. Thanks for this question, for this answer. Yeah, I think you should you have another meeting, right?
Yes. So yeah, thank you again for the opportunity, and happy to participate.
Thanks for participating in this panel discussion. Thanks. Okay. We next ask the Motasin. You can ask a question here.
Yeah, I'm Motasim. I'm from KAUST, and I would like to ask Professor Madry. So first of all, thanks for his talk and emphasizing on the role of the dataset and the leveling of dataset into the generalizability and robustness. But my question is what is the key important path to go? Is it trying to fix and build up new enhanced or what's so-called datasets? Or is it trying to design better loss functions, or in the sense of the robustness problems? Or is it even trying to introduce a new training schemes, or even designing better architectures, or transforming the problem into another domain, something like Fourier? Because I think the problem is just more complicated than looking to one of these factors independently. But what is the key path that one should tackle to at least to have a significant progress?
Sure, great question. So the answer will not be very kind of surprising. The answer is all of that. Essentially, in the end, so what our work showed, that definitely there is a work to be done in the context of datasets, that we need more rich and better annotated datasets. That's for sure. But this alone will not help. We have to have more algorithmic ways of improving our priors that our models have, and how to make them more human aligned. And this is a question in neuroscience in particular. And Professor Bethge in particular, Bethge, is working on this kind of stuff. And so there is a lot to be done there. It's if you think of humans, the amount of footage that that an infant is exposed to is not that much by our imaging standards. If you think of it, so they have something nice, our brains are good algorithms that are able to have they have some of course embedded prior, but also the algorithm that governs our learning has to do something right about enabling us to get this robust understanding of the concept. So to me, this field is very exciting, because exactly everywhere, we need to make advances. We are definitely at the beginning of the path. It just felt to us that people don't appreciate enough the data set aspect of it, and that's what we wanted to highlight. But doesn't mean that this is the only thing we should be focusing on.
Okay, thanks Professor Madry for answering this question. And we got another question for Professor Alan Yu. And the question is, for the adversarial attacks in the physical world, they're creating some adversarial patches. Do you think this one is somewhat related to your occlusion? You talk about occlusion. do you think like what's the relationship, and is there any common solution to solve both these two things, like say robust to occlusion and robust to adversarial attacks in the physical world at the same time?
I think they're very related problems. I mean, because, you know, if you take, you know, you modify patches a bit, they start looking like objects, etc. You know, certain patches perhaps a little bit more abstract. But yeah, I think they are very similar, and they, you know, they give rise to similar defense, you know, defense problems. You know, our own work has concentrated on defending against occlusion, and I think we haven't tried that out for defending against patches, but I think it would work reasonably well to defend against certain parts of patches. Although, yeah, we need to let you know by the end of the summer. So I agree with you, and I think similar defenses would probably be effective, though, you know, even what we've done is only limited. I think, you know, I think one needs, frankly, I think we need three-dimensional models. We need a whole lot of other stuff into these networks. So in terms of the earlier questions, I'm very much on the side of thinking that the current networks are not enough. We need a lot more inside them, as well as better data sets and better evaluation methods.
Okay, yeah, thanks Professor Allen for answering this question. I'm unmuted another person, Peng Rui Quan. You can ask your question here.
Hi, this is Peng Rui Quan from UCLA. I have a question for Professor Matthias. So in your talk, you illustrate many perspectives of adversarial examples. For instance, when we generate an adversarial examples of cat and we ask an image classifier to train on that examples, then the classifier start to memorize some image feature of a cat. And another perspective would be like the classifiers focus very much on the texture information instead of the shape information of a class. So I'm wondering from your perspectives, what is essentially causing the adversarial examples in the vision task?
I mean, I didn't intend to explain adversarial examples with this different biases for texture and shape. So I just highlighted a couple of differences between machine and human vision. And so texture and shape is two different types of cues that we can intuitively assess and we like to distinguish. And it's easy to, well, we can classify decision algorithms in their degree to what extent they are relying on texture information or on shape information. And there seems to be a tendency to using texture information, which is probably due to the fact also that texture gets a lot of pixel support, right? So you have a lot of input dimensions that define the texture, and it can be less precise. It's more like this back-off feature approach. And but I think the adversarial examples, they also look a little bit like the changes that you impose on the images also look a little texture-like, but I think there's so many room for all kinds of features that we don't quite understand that these networks can be using, that I think we are not really there in being able to explain what an adversarial example really is or what kind of decision rules used there.
Okay, thank you very much. I'm just wondering if we can understand a little bit more about the image features of the adversarial example. Perhaps we can utilize that features to design more efficient attack or defense mechanisms. But thank you very much for your illustrations.
Yes, thanks for asking a question, and also Professor Matthias for answering this one. I will unmute the Adam. Yeah, you can ask your question. Thanks.
Okay, cool. Thanks. Hi, I'm Adam. I'm a postdoc in Allen's lab. And It's really nice that Alan and Matthias kind of agree that we need generative models, and all of you three have said that we kind of don't evaluate discriminative models and we correctly, and it's like really difficult. Then on the other hand, if we want to have combined models like discriminative and generative models, then if we look at the generative model literature, they also really struggle on how to evaluate generative models correctly and how well they generalize. Now, if we have like combined or hybrid models, this would be like kind of double as difficult to evaluate. So is there any chance that we will be able to evaluate them correctly? Are there any opinions on this?
Well, like I think that actually, like in some ways, they are like, to me, generative models and like a real evaluation of discriminative models is kind of just two sides of the same coin. And in some ways, actually, if you were managed to kind of to like have like, so this is kind of the work we had, that like when you can use a classifier to actually get generative model, that actually might make it easier to to probe what they are missing. Okay? So if you can ask my classifier, oh, can you tell me what is your concept of a dog? Like, can you give me a random, like how a dog looks like, based on the features you have, and then you can see, okay, does it have, 4 paws or maybe some different number? Does it have 2 ears or some different number? Like essentially, like if you can ask this question to your classifier, it then actually makes it easier to evaluate in what way it might misalign with what you would like to do. So it might be one of the things that once you ask for more, it's actually easier to verify that it does what you want.
I see. Yes, but how will you ever be able to evaluate if it knows how all dogs in the world look like?
Well, that's the generative model what gives you. If you can sample from distribution of dogs, then essentially you will at least get an idea. Of course, not like this is a distribution. You will never be able to inspect it, all of its support, but at least you will be able to get some idea of like some, more significant trends.
Yeah, sure. So I think this would be like, for now, enough.
Well, I think that's where we should go. If it will be enough, that remains to be seen.
Thanks. Cool.
Yeah, Alan, do you have any comments on regarding this question?
I can talk with Adam about this on
Okay.
because I think you need to have a series of different questions or different tasks, and so having algorithms that don't just perform one task, don't just do well on ImageNet, but do well on transferring from ImageNet to some other data set, or which work on ImageNet and then also work if you change the background dramatically. So I think having that class of tasks are important. Another thing that was harder to say is that I mentioned adversarial examiners in the talk, but there's also the ideas of visual Turing tests that the Don Geeman and his brothers sort of talked about. Ultimately, you'd like to be able to answer any question about the image that a human could ask. And so if you could set up those types of challenging tests, that I think would be something which, as a person in the generative camp, I believe will demonstrate the values of the generative models. And so I think harder tests of that sort, and why I really like the adversarial stuff is because it sort of brings that out. You're not just testing on a fixed data set, you're sort of allowing other images to be created, that are not in your data set, and see if they mess up your algorithms. So I think we need to move a lot more in that direction. And I think, as a reviewer of some opinion paper I wrote said, the computer vision community has been incredibly lazy or not making challenges of that type. We're still working in this rather slightly boring, balanced training testing set, and that was great for the last 6 years or so, but I really think it's reached its sell-by date, and we need far more interesting and advanced types of tests to move forward.
Okay, thanks for answering this. Professor Matthias, do you have any other comments on this part, like how to properly evaluate those things? Hello, Professor Matthias. You can unmute yourself for answering this question. Do you have any comments on this?
I first understood you asking Madry, Professor Madry. I don't think I have a particular comment right now. Sorry.
Okay. Yeah. I also saw one question from Professor Tom Dietrich asked the question in the Slido. That's for Professor Alan Yu. How do you constrain an adversarial examiner to within the space of real image? Because you mentioned the adversarial examiner work.
Well, we've only had, I guess we've had one paper on that and another one, well, you can count on that, that's under review. I mean, the paper that I mentioned is one where you use computer graphics to generate the images. And computer graphics is very nice because you can control all the factors and you can vary viewpoint and so on systematically. And if you ask questions directly, I mean, by the algorithm we had or other better algorithms, you can sort of search through this enormous space in an intelligent way to try and find where the algorithms, break down. It does rely, admittedly, on being able to deal with computer graphics type stimuli, but on the other hand, as a believer in domain transfer, I'd almost say we should be requiring our algorithms not just to work on real images, but they also work on computer graphics images as well. So I don't really see that as a limitation. Do I care about absolute realism in putting patches on it? Well, I mean, I guess I would say as somebody who's half in the cog sci department, if a human can do it, I want the algorithms to do it also. So even if it doesn't look terribly realistic, but the human's got no trouble dealing with it, then I think the algorithms should be able to deal with it also. Because why can humans deal with it? Because potentially it's, it's an aspect of our visual system that's really good. And we ought to be having algorithms that have got the similar capabilities.
Okay, yeah, thanks Professor Allen for answering this question. We will let one audience ask the last question. Manju from IIT. Yeah, you can ask your question here. Yeah.
Okay, thank you. Thank you everyone for the great presentation. So my question is related to bias. So it might be more towards Professor Madry. So right now, I think many people are moving towards debiasing methods in developing models which are less, which can even handle bias scenarios. What do you think of that direction? Also, people are also trying to do some sort of disentanglement of trying to disentangle different factors and trying to get sort of concepts. And do you think will that help in sort of trying to find only suitable concepts so that it will not focus on unneeded concepts when you are doing this kind of disentangling operations? So my question is, what are your thoughts on those kind of approaches right now?
Well, they are definitely going the right direction, right? Disentanglement is kind of a word, this just means that we want to, we know that certain context should be disentangled, and they want our models to get that. So clearly, again, the moment we make the decision-making of our model more closely resemble ours, this is clearly a progress. The biasing approaches in general, especially in the context of fairness, of course, I would say their kind of scope goes beyond robustness, because in some ways they want to also debias things that even humans, or especially humans, have biases on. But yeah, again, this is a very important work, because that's what we need to do. We first need to diagnose biases, and again, I focus more on the biases of that correspond to human vision and kind of how human perception works. But there are others, so you need to have a toolkit to identify them. But then you need to think how to correct for them. So yeah, so I think this is exactly one of the key challenges machine learning right now is exactly like how to go beyond what we can just blindly infer from data. How can we be more retrospective about what we learn and adjusting it retroactively? So yeah, I'm very much looking forward to what this kind of strand of work will give us.
Okay, thank you.
Yeah, Professor Matthias Bethge, do you have any comments on adding this? Because the biases are kind of related to your CNN trained ImageNet trained CNNs are biased to texture, and you use some style transformation to make the model biased to shape.
Actually, I wanted rather to comment on the disentanglement. So I think if you think of scale invariance, so this is an operation that we know, a very simple one that applies to any object. So if you change the scale, it generates a lot of changes in the pixels, but the semantics stays exactly the same. And if you want to learn that from data in a typical ConvNet architecture, and you learn it for, say, 10 different object classes, it wouldn't generalize automatically to all kinds of other object classes, right? So the architecture is not designed that you can factor out the scale invariance directly. And so obviously one can impose such, say, scale equivariance in a hard-coded fashion. But it's one of these examples where when you understand invariance property that we are using all the time, if you want to learn that from data, it's actually quite tricky, and like factorizing out these transformations that suddenly allow you to generalize much more and reduce the learning complexity is, I think, an extremely important task, because in the end, learning is always like a combination of prior knowledge with data, and the amount of data we have is, even if it's 1 billion or more, it's really nothing compared to the curse of dimensionality. So we really need good symmetry assumptions and inductive biases, right? So I think we need more of exploring that.
Yeah, thanks for answering. Alan, do you have any more comments?
Well, I guess, infinite images, combinatorial explosions, I think finite data sets are out, no good, etc. But I'm probably repeating myself. I don't think that just having more data is going to help. Better algorithms are needed, better ways of testing performance are needed, richer classes, and like I think many of the other panelists, I believe that seeing what humans can do and understanding that is going to be very important, particularly if we want computer vision systems that work at human level, which frankly we're nowhere near, despite some people who are getting a bit overenthusiastic about it.
Okay, yeah. Okay, so yeah, thanks, Professor Alan, Professor Aleksander, Madry, Professor Earlence Fernandes, Professor Matthias Bethge for attending this panel discussing, and also for all audience for asking the question here and yeah, getting involved here. And yeah, the panel discussion now is over, and we next will be moved to the poster session.